And hello, welcome back to our little OpenFoam discussion. So in the last video, we were talking about changing the velocity boundary conditions. So this is what we want to fix our oil velocity boundary conditions as. No further change because everything is pretty much slip. So since we are done with that, we can take a look at the temperature boundary conditions, which is slightly more interesting than a fair bit more interesting than velocity boundary conditions. So again, we are left with all these generic boundary conditions that we want to change. Okay, so instead of you see this thing called bottom air 2, it's no longer called bottom air. We want to change it to oil because that's the region name. Okay, so what is this? What is a change dictionary how is OpenFoam going to read it when you run the change dictionary application? So it's going to say uniform internal field uniform 300. What is that meaning? It means that the internal temperature of the oil, it starts at a 300 Kelvin initial condition. So yeah, that's what we want in our simulation. So no change in that. Then it's going to say boundary field. Okay. First, it's going to say, okay, I'm going to take every single of these boundaries. I'm going to put a zero gradient there. Zero gradient means it's adiabatic, which for all intents and purposes is what we want. We want the box to be closed and all of that. We want all of this to be a closed system. So we don't want any heat to flow in or out. Perfect. However, it's also going to put a zero gradient condition on this oil to sphere boundary condition. So that's what we do not want. I mean and of course you have this processor boundary, which we already explained before. It's just for the what do you call that? Yeah. Hold on. Yeah, sorry, I had some distractions. Anyway, yeah. So this one we explained before already. And now this is for parallel processing, so we can just ignore it. We'll leave it as it should be. This instead, the next thing we want to replace is this thing called bottom air 2. Okay, bottom air 2 ... So in bottom air is the fluid region that this file was originally for. Now this fluid region is not called bottom air anymore, it's called oil. So we want to change it to oil 2. So what this star means here, it's oil to any other surface. For this case, this is oil to sphere. Okay, oil to sphere. So if you're not sure, well, of course, we can always copy and paste this whole thing here into this file here. And then we will just edit one at a time. Now this other boundary condition is very important for us to know. Okay, this will couple the temperature of the fluid to the temperature of the solid. Originally, it's called compressible turbulent temperature couple baffle mixed, whatever that is. Okay, then you'll have this T number, kappa method, and value. So let's take a look at what OpenFoam has to say about this particular boundary condition. So we look at the API guide on OpenFoam.com, the API guide for version 1912. That's when I'm making this video. This is basically a mixed boundary condition for temperature to be used for heat transfer in what do you call it? Back-to-back baffles. So this is originally, of course, for air, because air is compressible, sure, and basically this helps to specially to couple the fluid temperature to the solid temperature. That's what it is about. Of course, if you want to include radiation, you'll have this turbulent temperature radiation coupled mixed scalar field. Then you can refer to this here, but I'm not going to touch it just yet. I'll just leave it in the links in the comment section just for reference. Yeah, so this is the boundary condition we use for now. Of course, this is normally for air, but for the sake of we do things simply first just to explain. Yeah, normally our oil is of course incompressible, so why are we using this compressible boundary condition? Well, in the hot room case, I mean, you can argue it like that. The hot room case, it is basically air moving at very slow speeds, much less than 0.3 times the speed of sound. So, I mean, from that perspective, you can pretty much say that the air is incompressible. So that's a fluid. One way to look at the fluids. I mean, this is one of the tutorials, pretty good, but anyway, I digress. So, so what is the T number? This is the field. If you take a look at over here, what is this? How do you use it? T number is the name of the field, and kappa method is inherited from a thermocouple base. So you just leave that as it is. It says that, okay, I want to find the thing from fluid thermal, and the value I think should refer to the initial value, which is 300. So that's reasonable. Initial condition of 300 should be that should be the case. Okay, so I'll just leave it as it is to make things simple and for the sake of explanation. Okay, so that's the temperature boundary condition. So all I did was just to change this to oil 2, and I'll leave all of this constant. As to how to change the fluid properties of the oil, the heat transfer properties, later we can talk about it a little bit more, just before we run the whole thing. And where is this fluid thermal from? Yeah, that's another thing to discuss as well. There will be thermodynamic properties which you can actually specify elsewhere. I'll just show you where. It's in the constant file. Okay, the constant file, and you should have an oil thing here. Right now it only has a polymesh, but if you take a look at the bottom air, we can see thermophysical properties here, turbulence properties and radiation properties. So thermophysical properties is where you will want to define all your properties of the fluid. So that one we can do later. So right now we just concentrate on our boundary conditions first, because there's a fair bit of things to change. Alright, so next thing we want to take a look at is epsilon. So let's take a look at epsilon. Epsilon, remember, this is a turbulence property. Okay. Alright, so what is this change dictionary going to do? It's going to set value. There's this comment here. It says sets the value of all boundary conditions to non-zero, not to be used in simulations since zero gradient. Not used in simulation since zero gradient, only used in initialization. So yeah, we have this epsilon set to the uniform field of 0.01. I mean, while the uniform field here is already 0.01, there's no need to, I mean, this just ensures that epsilon field is at 0.01. Now we're not going to touch too much on this, what it should be, but just know that what this does is to replace every single value here with these two things, epsilon wall function as the type and the uniform 0.01 as the value. So it's going to replace all of these boundaries as this, and the processor boundary, it changes to type processor. Not going to touch too much on this issue because this is a turbulence thing. I don't want to complicate the discussion too much by going through every single little thing. Okay. Next thing. This is the K field, which is oops. Yeah, this is the K field, VIK. Okay, so this is the VI. I look at K. And again, it's going to replace everything with the KQR wall function, blah, blah, blah. Again, I want this to be a wall, so that's fine. And specifically for this case, I do not want to go and meddle with the what do you call it, turbulence parameters just yet. Just to keep this thing really simple. Just want to demonstrate what this change dictionary is all about. PRGH. PRGH. So yeah, let's go and look at PRGH. Okay, it is it's going to replace everything by this fixed flux pressure, uniform 1 times 10 to the 5. Okay, so this is pressure outside of hydrostatic pressure. Okay, so it's going to have the oil to sphere pressure also at the same thing, and of course the processor boundary will be type processor, as was said earlier. Okay, so yeah. So anyway, what does fixed flux pressure actually do? Fixed flux pressure, if you take a look, according to this OpenFoam.org guide, it says in the above example, it can be seen that all wall boundary conditions use a boundary condition named fixed flux pressure. This boundary condition is used in for pressure in situations where zero gradient is generally used, but where body forces such as gravity and surface tension are present in the solution equations. So is gravity and surface tension included? Yes. So we want to use the fixed flux pressure. So this boundary condition adjusts the gradient accordingly. Very convenient for us. So again, I'm going to put this link in the description below. Shouldn't be, hopefully it's not too intimidating so far. Next is this pressure boundary condition. Again, we have the same shenanigans going on. So same thing going on. VIP, blah 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 blah. Okay, same thing. So again, that's all well and good. And apparently for our air, or rather the original air change dictionary the oil, I mean the rho equation is not touched at all. The rho field is not touched at all, which may be good, meaning to say that perhaps it's not really used in this particular simulation. Maybe it is not used, but long and short of it, the summary is that we don't touch it. I mean, the original case doesn't touch it, so I'm just going to assume it is not important. Well, rho is actually for density, but we actually get our density from we also specify our density in our thermophysical properties, so you don't really need to worry too much about that at the moment, unless of course something goes wrong, then we can go and debug later on. Okay, so this is the oil. Next thing we want to look at is the sphere. So sphere is a solid, so I expect us to have to go and take a look at the boundary conditions for the solid. Okay, in a solid region. So what's a solid region for us? Oops, clear. CD. Let's go and look at either heater, left solid, or right solid. So let's go and look at heater, and let's look at the change dictionary. All right. So this is where we will have our reference for the sphere. Okay, and you want to copy this file over from here into the what do you call that? Sphere folder. So CPAR heater change dictionary into sphere, and just paste it there. CD sphere. Okay, so this is a change dictionary part. So let's go into here, change dictionary dict. Okay, so let's list again, and let's go to the sphere. I mean, all the stuff here is not going to be really touched at all. The only boundary conditions that matter are those inside the folder, so don't worry about all these things outside. Okay, sphere, and we'll take a look at boundary. Let's go to look at the T file, because that's the first thing that's actually done. Okay, so here we have min y, min z, and max min y, min z, and max z. We don't really touch any of these at the moment since there's only one boundary here. So since there's only one boundary here, I can pretty much just delete all of this. Okay, I'm gonna delete all of this. 1, 2, 3, 4. I'm just gonna leave an empty entry here. Shouldn't be an issue. Okay, so hopefully that doesn't give us bugs down the road, but if we do have bugs, then we can go and correct it later on. Okay, so good thing there's only one thing that we need to actually dabble with, and this is temperature. So temperature, we said we want our internal field to start at 500. We want 500 Kelvin to start our case off. So we have our internal field at 500. That's what we want to change here. Next thing we want to take a look at is the boundary field. So for boundary field, this means that whatever boundary field is given, we leave it as zero gradient uniform 300. We can leave that there. Usually that means that there's no heat flux across that boundary. It's an adiabatic boundary. So I'll just leave that there. It's kind of redundant. I can actually delete this because all I need to do is just have this entry, which I'm highlighting here. It says heater 2 ... is compressible turbulent temperature cover baffle mix. That's the only boundary field that I need to have. But you know, OpenFoam is just going to read this one first. It's going to read this entry. Then anything over here is going to replace, you know, the entry. So what OpenFoam is going to do, going to take this zero gradient uniform 300 and you'll replace it here. Then you'll say processor boundary. Okay, is there any processor boundary here? If not, then we'll just leave it. Next thing it's going to look is heater 2 ... And then it's going to search this one for heater 2 ... So since there's no heater, it's only a sphere, we are supposed to change this heater entry, because there's a region, this heater entry into a entry for sphere. Sphere 2 ... is going to be this. Okay, so that's the next part. So it's going to put compressible turbulent temperature cover baffle mixed. The T number, or that's the field, is T. Kappa method, solid thermal. So this is going to treat this as a solid. And in terms of for thermodynamic or thermal physical properties, whatever. And value, it should be starting at 500, not 300. Okay. Next entry here is a min y, which basically there's nothing here ever, so we can just delete it. If not, it will start adding this into here. So since there's nothing, we will just delete it. 1, 2, 3, 4, 5, and that's basically it for our boundary. Okay, so for now, it looks like we are set for both the change dictionary for oil and sphere. So basically all the other things don't really matter that much. The P and PRGH, take a look. For pressure, it is basically not very important, but of course we want a pressure here to be, you know, the same. I mean, if you want to be that stringent about it, we can actually just simply put our pressure fields here, not an issue. Okay, yeah, but of course we don't know whether this field is even going to be deleted. So let's take a look at the ORAN serial pre. Okay, so what's going to be deleted is nu t, alpha t, epsilon, k, u, and PRGH. So pressure is still going to be there. Okay, Q, quit. So pressure is gonna be there. U alpha T is not gonna be there. K epsilon is not gonna be there. Only P and rho. So okay, sorry, I should be looking at sphere. So anyway, yeah, I can just take a look at the P. Yeah. Anyway, I'm gonna continue this on in the next video. Reach 20 minutes, so I wanna go on yapping too much. But yeah, thanks for watching. I'll see you guys next time. Gonna upload all these changes to GitHub. Bye bye.